All right, there we go. Now we're recording. Okay, so just a reminder, recording this lecture, everybody, and I wanted you all to, I wanted to remind you all that not only are we recording this, but if you are watching synchronously or asynchronously, regardless of how you're watching this, I am going to be sending out a quiz on Canvas afterward. It's only going to be 2 short questions or so about this lecture, just to ensure that you are here, and that'll be your attendance credit this time around. And then other than that, I don't want to take any time, so I'm going to hand the presentation over to Jay Martin. He's our guest speaker today. He's actually brought quite a number of people from his team at Roblox. Jay is a data science manager at Roblox and has a lot of really cool work to talk about regarding, as you can see the title here, large-scale experimentation at Roblox. I have to admit, I have played a fair amount of Roblox and have enjoyed it quite a bit. So I'm excited to see what you're all talking about here today. And so Jay, you should be able to control everything. Let me know. I see Boris is here. Also, everybody now is a co-host from your team, so they can switch over if they'd like. But other than that, I am going to stop. And Jay, please take over.
Yeah, thanks, Brad.
And welcome.
Yeah, thank you for having us today. And Brad, when you say that you're familiar with Roblox, I'm guessing you might have a kid between the ages of 8 and maybe 14.
I have 2,
Yeah,
and I have played quite a bit. And I have to admit, I have played without them also. So I got started because of playing with my kids, but that's not the only time I have played Roblox.
That's great. Yeah, and so I don't know if a lot of people are familiar with Roblox, but we'll get into some more detail a little bit later so that you guys understand what Roblox is. So today, again, thank you for having us. I've brought the experimentation team from Roblox with me today to help me present on some of these topics. We're going to be talking about large-scale experimentation at Roblox, so I think it's a particularly apt topic for a data science class. So before we jump into today's lecture, I guess we're calling it, I wanted to introduce ourselves. So to start, my name is Jay Martin. I'm one of the data science managers here at Roblox. Prior to joining Roblox, I worked at Facebook doing research and development on advertising. I also worked at Netflix on original content, Stitch Fix on recommendations for e-commerce, things like clothing. And before that, I was going down the academic path, and I spent some time at NYU working in cognitive science. That's actually how I know Brad. And then before that, I was at UC Berkeley studying cognitive science and statistics.
Cool. Quick intro of myself. I'm Boris. I am currently the product manager for the experimentation platform team. In a very recent past life, I was a data scientist as well. Worked previously at Facebook, a small startup called NerdWallet, Capital One, and previously studied at UPenn.
Hi, everybody. My name is Vincent Su. I'm a data engineer here at Roblox. Prior to Roblox, I did a few different things, such as data science, data engineering at Salesforce. Prior to that, I was studying machine learning at CMU and then some nanotech research at Mizzou.
Hi, everybody. My name is Kelly. I'm a software engineer at Roblox. Prior to Roblox, I had application engineering stints at eBay, 23andMe, and Zynga. And before that, I finished my undergrad degree at UC Berkeley.
Hi everyone, I'm Xiao Chen. I'm a research scientist here. Prior to Roblox, I was doing time series forecasting at Uber Marketplace and also do Uber Maps ETA prediction. Prior to the industry, I was in like my PhD in academia doing causal inference with randomized experiments in Carnegie Mellon. And then before that, I was doing social network research in my master at Northwestern.
So we have a couple goals for today's presentation. The primary goal that we want to hope that everyone understands or takes away is what is the role of experimentation in the industry, specifically tech. And a kind of secondary goal would be we want to make sure that people in this audience understand how data science works. Sorry, is that me? Here's some background noise.
I don't know who that is. Let me see if I can mute everybody.
Yeah, so and a secondary goal for today's presentation is we want to understand, we want everyone to understand how data science works with other disciplines. So, data science doesn't happen in a vacuum in industry. You're working very closely with other disciplines like engineering and design. And so we want you guys to have that takeaway as well. But before we jump into today's core topic, we're going to give some background. I want to make sure everyone understands what Roblox is, because that's going to help give the context so that you understand like what experimentation is, how it looks like, and how it impacts our company. And because this is a data science course, I imagine that there's many people in this audience who maybe are considering pursuing a career in data science after they graduate. And so I kind of want to, even though it's not the main theme, I want to kind of hint on like, what does data science do in industry? Because I would imagine like a lot of people like hear a lot of things, but it's not exactly clear what data science looks like until you've done it. Cool. So Roblox is interesting. Like, what is Roblox? Roblox is actually a lot of things. And so what thought about it, it's a gaming company, but we don't actually create any games. And a way to kind of think about it is that maybe it's like a YouTube for games, because we have user generated content. So like people create games and put them on the platform. And even a more interesting way to think about Roblox is that it's a metaverse. And I know a lot of people probably haven't heard this term metaverse. And so I'm going to touch on it a little bit. So first, Roblox is a business. So Roblox is what we call a two-sided marketplace. And if you guys haven't heard this term, you guys are all very familiar with it. If you've ever used products like Uber, Airbnb, YouTube, these are all two-sided marketplaces. And the basic idea is that in a two-sided marketplace, you have a company that doesn't actually produce the good, but they're actually distributing the good. So it's like for Uber, you order a car, but Uber doesn't actually own those taxis or cabs or drivers. They're just playing the middleman role. Roblox is the same idea. We don't actually create the gaming content that we put on our platform. We actually have a gaming studio that enables developers to create 3D content. And so if you look on the left side of the slide here, you see our studio, and this is someone who's creating a new game, and you can see like kind of the different environment and experience they're creating for that user. And so after the developer creates a piece of content, they can publish it to our platform. And once they publish it to the platform, it's our job to actually generate the demand for that piece of content. We do that through a recommendation system, very similar to like Netflix or Amazon. We're trying to help find the right audience for this piece of content through personalization. So the question is like, well, then how does a company like this make money? We're not actually creating these products. We have a couple different revenue streams that help us pay our bills. One of the primary ones is that we actually have what's called the avatar shop. The avatar shop, so when the users are playing games on our platform, you actually have a character that represents you. It's called an avatar. And one of the ways we make money is that users actually want to customize their avatar and maybe like have different accessories. Maybe they want their character to have a purse or wings. There's also different kind of behaviors that you can actually purchase for your avatar, like dance moves and different things like that. So that's one of the ways that we make money. There's also in-game purchases. So sometimes you're in a game and you want to like level up or something like that. That's kind of like a related revenue stream. And then the other is Roblox Premium. And what Roblox Premium does is it enables users who pay more money to have access to exclusive parts of the platform, maybe some games that other users don't have access to, or let's say like other ways to like decorate their avatars. So what's much more interesting than as a business is that Roblox actually has a really grand, ambitious vision. We actually want to be the metaverse. And this is that term I referred to earlier. If you haven't heard of this, you might have some experience with the metaverse. If you've ever watched the movie Ready Player One, or read the book, or if there's a new book by the same author called Ready Player Two. There's also a book called Snow Crash by Neil Stephenson. These are all the metaverse. These are all different like people's vision for the metaverse. And the metaverse is basically this like idea that we can combine virtual reality, augmented reality, and reality into one single shared co-experience. And the idea is that we want to like break down those walls so that those lines become blurry. And we're a really long way away from this. So it's a really huge technological, hurdle that we have to jump, but this is the goal today. And this is actually really exciting. A lot of investors, like right now in Silicon Valley, a lot of the, tech billionaires, this is what they're trying to get a leap or a head start on, because whoever actually gets there first is going to be very profitable because they believe it's going to be the next wave of the internet. And so here on the bottom right of the screen, you can actually see a concert that we just hosted. That's Lil Nas X. And what's really interesting about this is that there's users from all over the world who are actually sitting in this game as a concert, in the concert from the seat of their own, like they're at home. They're actually experiencing this, Lil Nas X, larger than life. And so that's kind of like the very beginning stage of the metaverse. Obviously, it's, you can imagine how rich and exciting this can be once we actually have the technology in place. So, when you have such a large, ambitious vision for a company, you obviously have to have certain functions that are going to execute to get to this vision. And so, at a tech company, it's very standard to have certain functions. One of them is a product team. And what product teams do is anytime you've seen a change to a feature, like on Google or Facebook or Uber, whatever you're using, there's a product team that was responsible for making that feature change. And so their job is to actually understand the user, the person that's using the application, and come up with innovative ideas to improve your experience. And so they generate hypotheses about which features are going to be better. And then they work with the engineering team to actually build all that out. It's a very extensive process, probably a lot more involved than most people understand until you go into industry. And then along the way, we actually have a role called user experience, which their job is to understand how that's actually, this new feature is actually going to impede or improve the user's experience as they're working through the application. So they're really trying to understand the human element. Is this feature actually make things more difficult or easier to do? Last but not least, we have the data scientist. And so data scientist, as you all know, is a fairly kind of new creation in industry in the last decade or so. And the role of the data scientist is pretty unique. It's almost like the executive function of any team. And their job is to leverage big data, machine learning, and statistics to accelerate and automate decision-making at a company. And so, within the data science role, there's been a lot of bifurcation over the last 10 years. And so there's probably, when you hear data science, a lot of people now, when you talk to someone in industry, they'll be like, well, what do you mean? And so I kind of break it down a little bit because it's become increasingly specialized. Now we have roles like product analyst. Their job is to drive business strategy and improve the user, or actually understand the ecosystem that the user is experiencing through experimentation and analytics. We have a research scientist role. And what they do is they're usually more of a specialist who has some sort of special quantitative skill set, from academia. And we want to leverage that specialized skill set to improve solve a particularly difficult quantitative problem through research. And last but not least is a machine learning engineer. These are people that take some of the prototypes a research scientist might make about a new machine learning algorithm or some kind of new quantitative method. And they usually partner with that research scientist to actually bring that concept to reality into a production system that will actually interact with users. Boris.
Cool. So before we really dig into it, let's answer just a really simple question. Why do we even run experiments? Next slide. Yep, there we go. So let's say you're given a really simple decision to make. You are an employee at Roblox. You want to recommend games to our users. You have two choices. You have Ninja Legends and you have Kitty Raising Simulator. Ninjas are pretty cool. Kitties are pretty cute. How do you know which one is actually better? There's a couple things you could do. You could try to do some research. You could try to look at trends within kind of the user base today, see which is more popular. Maybe Ninja Legends ends up being the more popular of the two. But let's say it's so popular that it becomes redundant trying to recommend this. And everyone already knows about Ninja Legends. So people aren't really playing Roblox anymore if you recommend this. You often run into issues like this, translating some of the research that you have into a decision or an action that you can take after the fact. Sometimes you're limited, if you're building a car, you cannot go back and build a new car after the fact. So you have to live with that decision. But in software specifically, there is a big difference in that everything is reversible. If you look at a website, if you look at an app, at any point in time, it keeps changing and it's kind of an ever evolving kind of organism. So when you can reverse it, when you can kind of just try things out, that often becomes the most powerful tool you have for decision making, basically guess and check. Next slide. So let's say we did that. So we launched this feature. Let's say originally we had Kitty Raising Simulator. We tried out a switch to Ninja Legends as our recommendation. All of a sudden we see, hey, people are playing way more games on Roblox, or way longer, I should say. Massive success, mission accomplished, our job is done, right? But then what if I told you, click for the animation. What if I told you this was happening right as COVID started in April 2020? Could you really be confident that you managed to, I think, double the amount of time someone spent on Roblox just by switching out that game recommendation. COVID is a pretty rare situation. This is kind of once in a lifetime. But if you click again, you'll often find that there's always something going on. There might be a holiday around the corner. And a lot of times you'll have other teams who kind of are messing around, trying things out as well. And at a large company, you'll find that this happens multiple times a day. So there is no clean period you can really go and measure. And it makes it really hard to really just try something out, see how it goes, and then be confident that you actually had the impact that you thought you did. Next slide. So what do you do then? If you can't really have that kind of confidence, how can you be sure what the right decision is? And this is where we run into experimentation. So kind of similar to a science experiment, the key to experimenting for product development is that you need to control what the experience that user sees actually is. So let's say someone visits Roblox. When they visit Roblox, we have two choices. We can flip a coin, and let's say if it's heads, we show them Ninja Legends. If it's tails, we show them Kitty Raising Simulator. Over time, we get large populations on both sides. And if we compare the behaviors of those two populations, we can be confident that, hey, this was something that we actually caused. This was a difference because of the change that we made, because we're actually controlling the experience directly. Next slide. So what happens then? So let's say Ninja Legends wins. What do you do after this? Well, product development is usually a process of continuous improvement. So you don't stop after an experiment finishes. You might know that Ninja Legends is better than Kitty Raising Simulator, but do you know if it's better than Doge Raising Simulator? And then you run into the situation where you need to run another experiment again. And this keeps cycling back and forth. Every good experiment should hopefully lead to a new idea, a new hypothesis that you can test out. And the key to building a better product is just to keep going through that process of experimenting, trying things out, and generating new ideas repeatedly. Next slide. So a couple nuances about experiments in tech specifically, and even more specifically within software. They are usually massive scale. Like we're talking hundreds of millions of users on both sides. You have very high concurrency. So because experiments are so valuable, you want to run a lot of them. So you might have something like 1,000 experiments running at the same time. If you're using an app like Facebook or Uber. It sounds a little scary, but it is a very powerful tool for decision making. And it is extremely iterative. The faster that you can experiment, the faster you can get to a better experience for your users. So when we look at experimentation, next slide. When we look at such a powerful tool like experimentation, and because of how valuable it actually is, we want to do as many of these as we can. We want to do it as quickly as we can. So automation becomes incredibly important. So in practice, when we actually run experiments in industry, it's not just a one-off kind of do it ad hoc, try to set it up manually. You're essentially building automated systems to handle this entire process for you as much as possible. The human judgment comes in the interpretation, but when we actually talk about the process of running an experiment, all of these are done sort of programmatically. And this happens in roughly 4 steps, which we'll kind of touch on in a lot more detail throughout this presentation. But just at a super high level, one, you have to set up the experiment itself. So you need to actually build the experiences necessary and decide on the experiment you want to run. You actually have to randomly assign users into those experiences. This is what we call enrollment. And if you've never heard the term ETL, it stands for extract, transform, load. It's basically how you process data to get the results of your experiment. And then at the end of this, when you interpret it, you do run a series of statistical tests on it to help guide the interpretation of the experiment's success. And with that, hand it off to Kelly.
Yeah, so I'll be talking a little bit about how we as an application engineering team built some of the tools that we can use to accelerate the experiments that we can run and run more and more and more quickly. Next slide, please. So in addition to all of the requirements that Boris talked about, there's also some things that the engineering team cares about, because we need to make a system that can support the volume of experiments that Boris mentioned. And at Roblox scale, or at even larger companies like Facebook or Google, this gets to really, really large numbers. And there's a technical challenge to solve in order to get there. In addition, we have a ton of players on Roblox. We have to make sure we do what we can to scale the platform with the growth of the number of players. That's also a pretty major technical challenge. And we also want to make sure that an engineer that is building a feature or an experiment that's integrating with our system, that the effort that they have to spend is low, or as low as possible. The less time it takes them to do something, the faster they'll iterate and the faster they'll learn. And as a result, our platform will have made an impact towards their experimentation. Next slide. So let's talk about supporting as many experiments as possible. A really naive method of doing that might be to say, split your population into two groups, and one half of them gets some experiment, say A, and then the other half gets experiment B. And you'll notice any given player is only in one experiment. This is really simple, so that's a benefit. It's really easy to understand. The problem is you really can't run that many experiments. You can run two in this case, but the more you run, the fewer people you can test with. And that becomes difficult because you just won't have enough people to actually get any results in any reasonable amount of time. So this isn't really a great one. Let's take a look at another option on the next slide. All right, so let's say we remove the constraint where a player can only be in one experiment. Suddenly you have these overlapping experiments. A person can be both in experiment A and C and B and C. This allows for more experiments, which is good, but you're never going to be really sure, or not without a lot of work, if the reason maybe some experiment indicated, Ninja Legends was a better game, was it really because of experiment A, or maybe it was because of something that happened in experiment B? So that's not ideal either. Next slide, please. So instead of kind of taking either of those routes, there's kind of a combination that's been proposed in the industry and kind of championed by a lot of folks, including Google and Facebook. And it goes by different names. We've chosen the name layer, but essentially it's grouping experiments that affect the same feature area together. So for example, there are two feature areas in Roblox that are pretty well known. There's like the login flows and then the searching for game flows. If you grouped all of the login flows together so that a given player could only belong to one of them, you can feel relatively confident that those experiments won't affect each other on the same feature. Whereas it's also really unlikely that a login experiment will affect a search experiment. So you can group the search experiments together so the given player can be in one login experiment and one search experiment. So this is how we kind of combat high concurrency while limiting the amount of overlap we have for a given player. And this is kind of what we've chosen, and it's pretty well adopted in the industry. Next slide, please. Stepping back, one of the things that Boris alluded to was the idea that you have to randomly bucket people. But random is actually really tough. So what we do to visualize this, you might roll a die and say, well, a pair of dice. If your number's 2 through 6, then you go into experiment A. If your number is 9 through 11, this player goes into experiment B. And this randomization has to be pretty good, otherwise you'll get results that don't quite make sense, and it has to be pretty close to random. But this is the technique that pretty much the industry uses to put people into buckets. Next slide, please. There are different ways to create this random number. And one of the techniques is to use your standard programming language's random number generator. This is a very typical approach, but it has a downside because that random number generator, the random number that you generated has to be stored somewhere so that we can recall it when the same player enters the same experiment, right? Because we want to make sure that the same player always gets the same experiment every time they come back. Well, that's difficult because eventually we have to store that somewhere and recall it. And so when a new experiment is launched, what happens is every single player on Roblox suddenly, all at the same time, needs to roll a die, and we have to stuff the results into a database, some place to store it. With hundreds of millions of players, what ends up happening is we try to stuff hundreds of millions of records into our database all at the same time. And this happened for us quite a few times in early 2020. And the result is the database, the system that stores this information, can't keep up, falls over, and ends up bringing the rest of the application down. So this is bad. And this happened multiple times. We've had to figure out another way. And on the next slide, we'll talk about that. So instead of using a random number generator, what if instead we could do something that always calculates the same result given a specific input, like a player ID? this concept is kind of called a hash function. Hopefully folks have taken like an intro to CS class where they talk about hash maps or hash tables. This is the same thing. If we can take a player ID and maybe an experiment name or a layer name and run it through a function so that it always generates the same pseudo random number, we never have to store it, right? We can always just calculate it on the fly. And calculating it means we never have to store it in a database. And so that scales a lot better and avoids that database bottleneck. And so this is pretty much what we do. It saves a whole lot of computation and storage power. Next slide. One other thing we're trying to do is reduce the effort engineers have to go through to integrate with the experiment system. I'm going to illustrate kind of a naive approach, and we'll talk about maybe some of its downfalls. A naive approach might use that random number generator we had to roll a die and pick a variant or a treatment for a given experiment. It could be some identifier for the variant, usually a number, 0, 1, 2, 3. In code, that typically means some application engineer has to write a bunch of if statements, set a bunch of data, and then return the result. This is okay, and it's pretty easy to understand. But in this example, I'm setting the button size of some button to different sizes. What if I wanted to set a new size? I want to set a button size to 80 pixels tall or something. Well, I have to go cut a branch in my source control, make the code change, get it reviewed by a colleague, merge it to mainline development, deploy the change. That might take 3, 4, 5 days. So, some companies don't release their changes very frequently, so it might take you a month. That's a pretty slow iteration cycle. And so we think we have a better solution. Next slide, please. Instead of the random number generation system returning a variant or treatment identifier like a number, what if we actually return the actual value? In this case, the number of pixels large we want the button to be. So it could be 20, it could be 40, it could be 80. It simplifies the code, and provides a lot more flexibility for us to introduce new variants and new treatments. In addition, it allows us to do other things like maybe we change 2 variables at the same time. So now you have different combinations of different parameters changing their value. And so we get multivariate experiments for free. It also means it doesn't have to be a human choosing these values. Maybe we could have a machine learning algorithm pick a new combination of parameters and values that we could use and see if that works. So this is heavily adopted from a paper published by Facebook on the plan-out language. And I'll talk about that in the next slide. So we've got these variables, we've got these values. We need some way of being precise about specifying it. So this is where we kind of merge the last slide about parameterized values with the hash functions we talked about earlier. Using this plan-out language, it heavily leverages hashing to take a given input and use that to create a random number that you can use to then pick one of the choices. So if you look at that blue line that says button size equal and the function uniform choice, we're saying we want to pick either 10 pixels or 20 pixels based on the hash result from the input unit user ID. So what that means is for the same user, you always get the same output, but different users should be split evenly between 10 pixels and 20. Next slide, please. So we kind of talked about those engineering requirements, right? We got high volume experiments. We're going to use layers to manage that. We need to scale with the number of players. So we don't want a database. We're going to use hashes in order to get kind of pseudo randomization. And we're going to reduce the engineering costs by using parameterized experiment variables through plan-out. Next slide. So just a really, really brief overview of the pieces that we have to build. You need a system to create the experiment or define it, author it, usually some sort of web UI. You plug it in, hit save. And then after you save it, you need some way to publish it. So usually what this means is some sort of process that moves the data and the experiment definitions you've authored into a production environment where all of the players of Roblox are now exposed to it. At some point, that data needs to be exposed to other app servers and mobile apps within the Roblox ecosystem, and that's what we call application integration. Usually it involves providing an API or some other method of accessing this data, sometimes through a CDN or content distribution network. And the last piece, and this part is really important, we need to track the behavior of the players who have been enrolled into one of these experiments, right? So anytime a player clicks on a game to play, enters a new search term, is enrolled into a specific experiment and treatment, we need to send that into some system so we can track that data and analyze it later. And that's the part that Vincent will be talking about next.
Awesome. So in this section, I'll walk you through an example kind of describing how the data is being collected and processed into human readable insight for analysis. Don't pay too much attention on the text in this diagram right here, but it's something that we call data pipelines. And usually in the industry, once you have the data, for example, you have the experiment set up, right? We start logging all the information every time you log in, you search something, an event is generated. So that data goes somewhere, right? It's all scattered around the system. So we build this automated scalable data pipelines to pick up those pieces of data, we combine them and process them through this entire thing so that we don't have to manually involve ourselves into that. And here you can see things are running in parallel, right? The first line, for example, is fully in charge of the feature for the login page. And the second line would be the pipeline in charge of the search function. And the third one for the shop where our users get to buy virtual items for their avatar, for example. Next slide, please. So we'll use the same example we mentioned earlier. Now we have two games we want to recommend to the new user. We want to see which one to recommend to the new user so that we get more engagement out of them. In the example, we will use playtime, for example. Next slide. So one piece of the data that we have from the users is enrollment. As earlier we mentioned, enrollment is basically which user falls into which experiment or the variant. A variant is different choices that we have inside that experiment. We'll go through this in the lenses of two users. The user number one, highlighted in blue, Meow284, they're hashed into the Ninja variant, meaning we will always show them the Ninja Legend game when they log in. And the second user, I Love Kitties, highlighted in red, in yellow. This user is hashed into the Kitten variant, so that every time they log in, we'll show them the game where you get to raise pets. Right, so we have the data for the, so we aggregate this, for example, on a daily basis. We will know for all the users we have who touch on this feature area, what experiments they are enrolling into and what variant they're hashed into. And next, we have the metric data. So these are the actual pieces of data we care about, such as your playtime, your click-through rates on the page, how many items you have bought, or how many times you change your avatar clothing. These are the actual things that we want to seek to improve. Right, so now we can see the same users, Meow284, I Love Kitties. We get to see their playtime in real time, right? So day one, Meow284 play only half an hour. On day two, they played 0.7 hour. On the contrary, you can see I Love Kitties is spending quite a bit of time on Roblox playing the pet racing game, right? Maybe we should send a notification to the parent, but we don't know, right? Next slide. And right here, is where we combine data from different sources. It's something that we do a lot in the data engineering world. Again, as mentioned earlier, we have data scattered around in different places, sometimes in different databases or different technologies entirely. That's why we try to combine them to get a bigger picture and better sense of what the data, what the story the data is telling. So here we see same two users. We can see in this same result which variant they're hashed into, and also all the metrics that are associated with that user. Next slide, please. But having daily information doesn't really matter, right? Because what we are doing here is not just to have some sort of insight to plot the trends or whatnot. Those are useful things to do. But in the case of experiment, we actually want to know which variant actually turns out to be better, right, for the entire experiment. So what we do is something that we call further aggregation. For example, we aggregate across time. Across time here, meaning we aggregate across the entire duration of the experiment. So here we are actually getting rid of the date column in this example, right? I only care about for each user for the entire duration of this experiment that you're enrolled into. Tell me the total playtime, right? You can do different kinds of aggregation functions. You can calculate the average, the percentile, or most commonly the sum of the metrics. So here we have the total playtime across, example, 2 days. Right, for those two users. Next slide, please. So at this point, we have your user level data, right, aggregated across the entire duration of the experiment. It's a great set of complete data that we can run analysis on, right? We can directly send that through our stats models to run our t-tests or any kind of questions we want to ask out of the data. The problem is we only have limited amount of compute resources, right? Even if we're running on the cloud, well, we still have to be conscious of the time it takes to run those things, and even if, and whether the machines have enough memory, right, to process the data. That's why in industry, a lot of times we have to reduce the amount of data we actually send through the final modeling process. And what we want to do here is to find a sweet spot between precision, right, the insight we can get from the data, and also the cost of the computation. So here in this step compression, what we do, if you look at column number 4, for example, we are basically defining a method to compress the data. You can think of this as bucketing, right? Instead of having all the records we want and run them through the model, we try to put them into different buckets so that in the end, we have smaller amount of buckets to run through the algorithm. In the example, we take a look at the single variant ninja, right? And the playtime metric. If you look at the first row, let's say we have 1,000 users, right? All of them played for the entire duration of the experiment between 20 to 21 hours. I don't really care whether you play 20.1, 20.5, right? I want to aggregate this information somehow. So what I do is I just say, okay, let me use the flooring method for the integer. So if you're playing the game or on Roblox between 20 to 21 hours, I would just put it in this bucket. And same thing for those who are playing between 30 to 31. And at the end of the day, what we have, instead of having 3,000 rows, right, in this example, we have effectively reduced that into 2 rows. And that's a significant amount of reduction of the data while preserving the information you have from the data. Next slide, please. So going back to the flow of the data pipeline, right? We have the data aggregation step where we have the metrics information, the enrollment information, we combine them at the user level. So at a daily basis, we have the complete picture of what each user is doing and which variant of the experiment they're hashed into. Next slide, please. And we have then the rolling aggregation across time, right? Because we don't really care about the daily information individually. What we care about is the data for the entire duration of the experiment. So we roll them up, we aggregate them. And next slide. To be able to run computation across this gigantic amount of data with limited resources, we compress them, finding the balance between the precision, the insight we can get, and also the compute cost in terms of memory, storage, or the time, right? Because you don't want to run a daily job for 1 week, then you will be put behind. And next part, my colleague Xiaochen will walk you through the magic behind the stat models.
Excellent. For this part, I'm going to cover how we use statistical learning to drive business product decisions. I think the first question is to ask is, why do we need stats learning? And what is the problem we try to solve? Next slide, please. So I use an example to illustrate this, to motivate the statistical learning. So for example, if our Roblox avatar team wants to add an additional list of new avatars, the purpose is to increase the players' happiness and engagement of them. So we divide the sample users, sample players into 2 variant groups. Variant A has a new avatar list and variant B has the old list. So after we run a few experiments, we want to collect the data, compare our goal metrics, which is the engagement. We use average daily playtime, and we find out, next slide, please. If we find out variant A has obviously a larger average daily playtime than variant B, can we conclude that by adding a few new avatars, these few new avatars, we are able to increase the engagement of users? Or is it possible that this is happening by chance? So here comes our problem. How do we define by chance? Next slide, please. A more simple and illustrative example is think about if you want to flip 10 coins and you end up getting 8 heads and 2 tails. Obviously, you have 0.8. You have 80% of getting the heads. This is different from your expectation of 50% of fair coin flips. So can you conclude from there saying it's a biased coin, or this is totally happening by chance? They are still fair coin, not biased. So in order to answer this question, statisticians developed hypothesis testing framework and p-values to answer it. Under the framework, you're formulating your problem by two hypotheses. In this example, there is a null hypothesis, which means the coins are fair. So the probability of getting a heads is 0.5. And there is another alternative hypothesis, which is the coins are biased. So probability of getting heads is not equal to 0.5. Then based on your observations, you calculate output called p-values. This quantity describes how extreme your observation is given that your null hypothesis is correct. So put it in more plain English, using the example is in your case, if you calculate your p-values based on your chance of 0.8% getting a heads, and this p-value shows you if your assumption of the fair coin is correct, how likely you're getting this 0.8 heads probability. So if p-value calculated is extremely small, that means if the coins are fair, it's very unlikely that you'll get 0.8, like 80% of heads. So then you can reject your null hypothesis of a fair coin. You conclude that this is a biased coin. So this is how hypothesis testing and p-value works. So these are useful tools to analyze experiments and drive business conclusions in industry. But in reality, we might have more complicated adjustment of the analysis. Next slide, please. Next slide, please. Thanks. So, or what are the complications? One of the complications I want to talk about is the multi-comparison issue. So previously, we only talked about two variant group comparison on a single goal metric, but in reality, we might have multiple comparison group. Like for example, we used to have like two lists of avatars, one small list and one large list. We might be interested in adding a medium-sized list. And on the other hand, we might not only want to see one goal metric, the average daily playtime, but we also interested in looking at the revenue as another goal metric. So in this case, we have 3 comparison among all the variant groups. We also have 2 goal metrics. So basically, this is like a 6 number of tests for a single experiment. So in the multi-test cases, how we arrive at the business conclusion is we'll consider the experiment as a success when seeing at least one success among all the multiple tests. So then the definition of happening by chance will be different than the single test definition of happening by chance. Next slide, please. Let me explain this. Going back to our conflict example, if you flip one coin, it's like you're running single test to variance comparison on single metric. And this time by chance means 50% of getting ahead. Yeah, and by if we think about flipping multiple coins simultaneously, we're doing multiple tests. And we claim at least one head as a success, the same thing as we did for the multi-test in our business scenario. So in this case, in the multi-test case, the probability of by chance is much larger. By doing some simple math, this like 50-50 becomes 97%, and which means 97% of the time something happening by chance. So we need to correct for it. Next slide, please. Our Roblox experimentation system automatically correct the multi-test issue. So we correct multi-test p-value threshold by the classical 2 method, which are Bafferoni and FDR, which stands for false discovery rate. I won't go much in technical details to explain those terms. If you're interested, feel free to search online. There are tons of materials. So, but bottom line is because we always have to adjust our p-value threshold whenever there is another metric or another variant, adding metrics or adding variant is not free. We have to be super cautious about it. Next slide, please. The second complication, the second complicated adjustment to our analysis is when how users respond to the variant change can change over time. So this dynamic behavior mainly results in two problems. The first problem is the user novelty effect. Next slide, please. So when people, what is a user novelty effect is when people see a new feature like a button or a new, another new product, they usually feel tempted to click on it, play with it because it's new and fresh. And in the short term, it might boost our engagement if the engagement is a result, is a go metric. But after a while, when they are more adapting to it, the behavior converges. Next slide, please. The second problem is a long-term effect, usually happening more than a few weeks. So think about the example when if we decided to launch a restriction to number of hours that people can play in each day. In the short term, it might make people play less because it's actually a hard restriction, right? But in the long term, it might actually increase the playtime. Why is that? Because we don't allow people to abusively play the game. So they're adopting more healthy behavior. So they play more regularly, but more in long term, in which way we might be better at keeping our customers. And we want to, we want our system to enable such ability to measure the long-term effect. So next slide, please. What are our solutions to these two problems? For the first problem, the user novelty effect, we choose to either estimate the novelty period using more complex behavior models, or we just drop the first data point and focus on more stable behavior of users. For the long-term effect, we periodically create a group of users that are held out from the product launches or product experiment so that we can measure after a much longer period for the long-term effect. So these are our two solutions. Next slide, please. So in the last part, I want to give you some more complex cases of experiment setup. Next slide, please. The first complicated setup is related to volatility. When I say volatility, it means like higher volatility indicates your sampled user of the experiment are more different from each other. So if you look at the distribution of the goal metric, like a playtime or other goal metrics you're interested in measuring for that experiment, it is more spread out. And high volatility, as the title says, it decreases your power of tests. And for power of tests, we define it as given there is a difference between the two variant group, how easy we are able to detect it. So here, if we look at the two simulated examples, there is a left and right graph in two different cases. In both cases, there are two variant group of users. The true difference between them are the same, but the volatilities are different. So the left group is more spread it out. So there is a high volatility. On the right group, on the right side, the right cases is more condensed. So the denser population, denser distribution means low volatility. It's very obvious that the second graph on the right is much easier to differentiate. There is a difference between the two groups, right? So which means low volatility allow us to make the detection easier and increase the power of tests. So in reality, that's why we want to have some mechanism to automatically decrease the volatility of our experiment. How do we do that? Next slide, please. So our solution to the high volatility cases is by implementing the automatic variance reduction techniques. So basically, we lower the volatility by comparing more similar users using the block design. It's a two-step. The first step, we grouping the similar users into blocks. And in the second step, we estimate the variance difference within each block and average them. And there are theoretical proof saying that in this way, the volatility, the variance is much smaller. So that's why the power, we have a larger power in this block design. Next slide, please. The next thing I'm going to talk about as a more complicated case is the network effect. So since Roblox players is a highly social interactive network effect arises because if the users are connected to each other, there's a high level of interference between different variant groups of users. For example, if you think about yourself in the variant A, as in the right graph shows, the red group is variant A, and you're one of them. And you are recommended a new game because all the red group users are recommended a new game. The gray group, which is in variant B, doesn't. But you co-play with your friend who is in variant B, the gray group in the graph. Even though you two are randomly assigned to different variant groups, A and B, you two are exposed to the new game recommendations. You can see from the graph that all gray users are connected to one or two red users. So the whole network is exposed to the recommendation of the new game. If you compare the metric difference between the two groups, it's very unlikely that you don't see a difference because all of them are exposed. So the question is, how do we cut the network interference between different variants of users? Next slide, please. So there are two available methods. I just list two. One method is a multi-level design. We call it cluster alignment, which means, so basically if we put it into 3 steps, is we first divide the network into clusters. And the second step, we randomly assign variant to clusters. To notice here is cluster, but not users within the cluster. In the third step, we assign the same variant to all users within the same cluster. So in this way, we ensure that the same network cluster are in all the users within the same network cluster are in the same variant group. So in this way, we can cut the interference between the two variant groups users. The second method is called switchback experiment in industry. So the method's idea is to switch the variant state of the whole network from period to period. But at a specific point in time, you keep all the users within the whole network in the same variant. So these are two methods with pros and cons, and many times which one to choose from depends on also your availability of your engineering system. And that's it for the space learning part.
All right, just a quick recap for everyone. I know we go into a lot of details, so just a couple quick highlights. One, data scientists are a critical part of any well-functioning product team, and specifically the role of a data scientist is to guide decision-making and help build a better product. When we make decisions as data scientists, experiments are one of our most powerful tools because they help us establish causal relationships and build confidence in the effects and kind of changes that we actually observe. When we go to run experiments, in industry, it tends to happen at very large scale and it relies heavily on automation. These automated systems are built by very large cross-functional teams. And at a very high level, there's kind of a couple challenges to that kind of automation. One is just how do you do the randomization for the different user experiences? Getting experiment data at large scale itself is a challenge. And this is one of the unique disciplines of data engineering. And then the last is how we correctly interpret experiment results. There's oftentimes complications in life that make things a little more difficult. And we want to create systems that allow people to make decisions very safely and not have to think about this a lot. So a lot of this is built into the design of our interpretation and our analysis systems. And with that, that concludes our kind of scheduled programming. So we'll open it up to Q&A.
All right, fantastic, thanks. So let's see. People can ask questions in the chat and we could try and moderate those for you all. So the first one here is Alexander. How does data collection comply with COPPA? Do you mean HIPAA?
No, COPPA, he's right.
Oh, COPPA, sorry.
So I guess I worked on this issue quite a bit before. There's a couple different ways
great question.
to do it. And it is a very complicated and kind of
real quick, should we
area.
define what COPA is for the audience in case?
Oh yeah, sure.
Is it the Children's
Online Privacy Protection Act?
Yeah, something like that. Yeah.
Basically, and this is happening across the world. So there's the California Consumers Protection Act. There's also GDPR. These might be kind of terms that you hear floating around. The theme that kind of unifies this is that there are rules and regulations now on data collection. And it usually comes in kind of two forms. One is how closely you can tie to a specific person. So usually when we talk about data collection, there's kind of, you can think of like two rough buckets. There's what we call anonymized data, which is if data comes in, we know that, let's say Roblox is still up and running. We don't collect your user data. We don't know who it is that's hitting Roblox. We just know that, hey, Roblox successfully loaded the page for you. And then there's kind of richer data that we use for things like personalization. In compliance, one of the major kind of tools companies use is to move this kind of rich user data into a more anonymized format for longer term retention. And this helps with compliance and also helps kind of preserve privacy so that you can still operate your product, but then not be creepy about knowing exactly which user it is that you're looking at. There are also specific requirements for what we call right to be forgotten, which is the deletion of data and how long you can store this. Usually this also happens with automated systems. So after a certain period, there's any data that you kind of store has a record of when it comes in, and you essentially would purge that data after a certain period of time.
All right, we have another question from William. For new hires, what tends to be the biggest difference in terms of expectation versus reality in terms of what the job's actually like? What are the major pitfalls for new hires, if any?
For all the roles, or?
Boris or Xiao Chen, or also are people interested in the engineering misconceptions as well?
Yeah, let's go back to the data engineering in a bit. I'm assuming here that we're going to be talking about like junior data scientist roles. So people that you'd be hiring directly out of undergraduate that may not have graduate experience, right? So when we created the undergraduate data science major, the goal of what we're trying to do here is to make sure that our students can land data science jobs and be successful at them without having to go through, without needing necessarily to go to a master's PhD program, right? We want to arm them with the skills needed, but what would, in those cases, what would be, what do you see in terms of experience and skill sets, new hires potentially lacking that'll be like the biggest, difficulty for them in those first critical 90 days of the job?
Like Boris already has a response ready to go.
I have one take on this, but I think everyone will give a different answer. So happy to kind of shop this around after. I think the biggest difference probably is mentality. So when you are working, the point is not necessarily to use a specific technique or do something that's very sophisticated. The point is just to solve a specific problem. A lot of times it's just the simplest version of what solves that problem is what works best. I think a lot of times when you're learning, it does help to kind of push the boundaries a lot more, get into a lot of areas that you maybe be less familiar with and kind of get broader exposure. It's not necessary oftentimes to kind of show off that knowledge, I think, when you're actually starting to work. In general, most, I think, tech companies now are pretty flat organization. You never have to prove that like you're worthy of being in that company. That would be a horrible culture to be kind of working in. Everyone assumes you're a smart person. We're all just here to kind of solve problems together. So I would say just that mentality shift of like, hey, how do I go solve a specific product or business problem? And then the skill sets that you kind of learn are just there to support you in a way to actually get to that solution. Mentality switch, I would say, is probably like the first thing that I would recommend kind of people getting into the mindset of, but also just be aware, like data science is such a broad field. And to be honest, like it changes so quickly. Like when I graduated, most of the Python libraries didn't even exist, like 8 years ago, something like that. So you're going to have to learn as you go. And I would just say like, keep a really open mind. What we say today may not be the case 2 years from now.
It was definitely difficult.
I would like to add to that in terms of data engineering new hires, is that this field often is like a shape shift kind of a field, because you don't really just work on pipelines, for example, because different roles, different teams, different companies, when they say data engineering or sometimes even software engineering, you work with data, you actually touch on different components. So for example, one day you might be building some SQL pipelines to process data, and other days you might be building maybe a dashboard to surface the data to you, the data scientists or the product managers. And maybe on the third day, you will be writing some sort of Java code to plug in some custom logic into your data pipeline. So I would say a lot of things that you learn in undergrad and stats classes, comp sci, all those capabilities that you have would be something great to have for data engineering. And just like other engineering fields, right? I think what Boris mentioned about mentality is definitely one of the most important parts, being able to learn, right? And also learn from first principle, because there are a lot of data technologies out there, right? You've probably heard of Kafka, you've probably heard of Cassandra, and there's MapReduce and then Spark. People are using all kinds of different technologies, but the key thing really is not about, I know Kafka inside and out, I'm gonna use it to solve every single processing problem. But really, you go from the problem perspective and you go about, okay, what are the constraints of the system? What are the requirements of the system? And then what kind of technology, not necessarily what technology, but what kind of technologies do I need to use to solve this problem? How do I stack them together? And then you go and look for what's currently out there in terms of the open source tools, or maybe we need to build something in-house.
Oh, you muted.
Sorry, yeah, I hit the space button, but the kind of capability to learn from first principle, understanding kind of, for example, where you need to use stream processing, where you need to batch processing, and what is eventual consistency, data availability, what happens when your system goes down. Those kind of things really help you make decisions, and as you progress in your career, those are what help you guide the team.
So I wanted to actually build on that and say that what Boris, you were saying earlier also makes teaching data science difficult at the undergraduate level. They've got 4 years here, and by the tech stack from when they start to 4 years later when they're leaving looks very different because the field moves very quickly. So the program, the educational program has to be pretty nimble too. Giving students hands-on experience with solving business relevant problems is hard also, right? So I've seen this a lot as well. What both of you have alluded to, which is like, new hires kind of want to show off their technical chops and sort of, it's that mental shift of, oftentimes simple is better than complex for solving business relevant problems. That shift is hard to get people to undergo. It's a hard mental change, especially from undergraduate where everything is like you're focused on grades and like doing the everything like as best as possible. And in business, you want to do as best as possible, but also you want to get it right and quickly, oftentimes. So there's definitely a mentality change. So in terms of that, well, actually, I'll kick it over to. There's another question, which is there a set of data science interview questions that we should be especially prepared for? It seems like it's hard because that seems like the answer is it depends. Every company is different, but I guess relevant to what you all are doing, like what does a data science interview look like for a junior data scientist?
So I'll speak just to Roblox specifically, and every company has a different philosophy, I think, on how they do interviewing. And to add one caveat to that as well, and I know this makes it even more complicated, there are kind of different roles within data science, like Jay mentioned at the beginning of our conversation. So depending on what specific kind of flavor of data science you're really looking for, are you a builder or are you someone here to understand? That may change the interview itself. But generally, there is going to be a tech screen for any kind of required skill sets. I would say for the tech screen, it's usually more of a binary, like either you are capable of doing and kind of being self-sufficient and doing everything that's necessary, or you aren't. It's, I guess, another way to think of it as like, it's a survival skill set. Either you can survive or you might kind of struggle a little bit. For the areas outside of that, like if it was someone who's more of a generalist looking for product understanding, a lot of it is going to be more open-ended. Do you have good product sense? Can you frame the right questions around some of these things? If we're talking about building, let's say like inference systems, it'll get a lot more deeply technical. But for a junior role in general, the overarching theme would be, it's more about how you think and how quickly you can learn a lot of things than specifically how what the corpus of knowledge you currently absorb is.
I think I'll add to a specific question like an interview preparation. So when asked about like a set of questions, I think if you search online, there are a lot of like search lists and you can prepare the list. Another way is to prepare not only your knowledge about data science, but your mindset. Basically, I think a good way to practice, my recommendation is whenever you have some problem or you have some observations, think about how are you going to prove it, what data are you going to collect. So it is not limited to the company you are applying for. It may be from daily life, something like that. I think it's a good practice. And if you don't know the answer, you can search online and also ask people around you who are in the data science community. They might know it a lot. And also as a junior data scientist into the company, already enter the company, it's good practice to talk to people and regular check your.
One thing actually Sachin touched on, which I probably missed in kind of so William or someone's earlier question about, I guess part of the mental shift is like data collection oftentimes is one of the hardest things in data science. And it's actually very powerful getting data collection right. Like really early, I think my first job out of college, I think at one point I had to build a spend prediction model to infer how much someone would be spending on credit cards. And it ended up that like, if you literally survey a user, you will get a more accurate response. So there are cases like this where the data itself oftentimes is more valuable than anything you can do to it. And this is kind of a common refrain as well. Like if you ever hear kind of like a Google search team talk, it's not that Google search does search better, it's that they have probably 100 times more data than everyone else.
All right, thanks. We'll do like a couple more questions. There's Sergio, do you want to go ahead and unmute and ask yours? You had your hand raised.
Thank you. This is more a question, for example, for us as students. As y'all work already in industry, I'd like to know what are certain skills that you'd consider most important for someone in our position to learn, meanwhile we're still in college, to join the industry. For example, the best coding languages to learn and certain skills that you would recommend?
I guess if this was coming from a software angle, your choice of language in most jobs actually doesn't matter. And in fact, most interview processes will allow you to pick the language you're most comfortable with for almost any technical role. So in that sense, what we're looking for more, if you're talking about a software or even a data science, data engineering role, is familiarity with the tools that you do say you know, and the ability to use those tools to solve problems. And that's kind of abstract, but at least that's my point of view.
One thing to add to Kelly's point is there's probably like buckets of skill sets that are kind of interchangeable. So like if you're choosing between Python or R, like it doesn't actually matter. As long as you know something in that vein, that's fine. But one thing I think people often miss is just like knowing how to do large scale database operations. When we talk about kind of massive scale data, like we're talking potentially trillions of rows of data, and interacting with data at that scale usually has a specific set of technologies. There's specific query engines for this. You might hear some of these buzzwords like Spark or like Hive, MapReduce, which is the thing that actually powers Hive. All of these usually have a SQL-like interface today. It wasn't always the case. Once upon a time, you had to learn things like Pig, but I would not recommend that anymore. But knowing how to do database operations is important. Data munging is kind of an indispensable skill, and probably the one skill that is most commonly lacking from kind of profiles that we see.
Again, this kind of goes back to the, in my opinion, overemphasis on the like programming languages, and like machine learning. Undergraduates in data science all want to learn like machine learning and deep learning and like all this stuff. And at the end of the day, most of the job is data cleaning. And if you're actually very good at learning how to like clean and quickly clean and work through data, that's a very valuable skill, because that's what most of the job tends to end up being. So there's, okay, you're answering some of the questions. We'll do this one last question in here, which was from Meta. How important is domain knowledge, which we already discussed a little bit, but they say, would a data scientist at Roblox be more successful if they'd also studied video game design? And sort of the follow-up to that is like, how can a data scientist kind of switch from one field to the other?
When you say switch fields, what specifically, like from data science to data
I
engineering?
think switch
or
between,
engineering?
yeah, like just between companies, let's say. Like if you're working at a company like Facebook that has different problems, as a data scientists are often working on different problems than you might at, like, you know, Roblox, right? Or Uber, companies you've talked about here, right? So I think the technical skills probably are still translatable, but like how do you kind of pick up that domain knowledge?
Anyone want to jump in on that? Yeah, so I think the trade-off between breadth and depth is a complicated one. I think it's the same as like when you think about like medicine, and there's some doctors that are generalists and there's some doctors that are specialists. And the same kind of situation plays out in data science, where you know, by becoming a specialist, you can get paid more and do kind of a little bit more thought to be sexier work, but you limit your, like, the kind of jobs you have access to, because it really requires that like that company has that specialized problem. And so it's kind of like this general trade-off. We have really strong generalists who are really good. You can plug them in. They can solve problems, you know, general problems across the business, but it might not be a super deep solution, but it gets us 80% of the way there. And that's pretty good most of the time. And then there's other people that like really go deep, like maybe have really deep academic backgrounds and specialize. Like, for example, Xiao Chen, she has her PhD in large scale experimentation. And so we have her here as a specialist to really go deep in helping us solve our experimentation problems. But very few companies in the world actually do large scale experimentation. That's changing as the internet's becoming more and more prevalent and more stores are going online after COVID. But like, so it's kind of like a career decision, like, you know, more about like, you know, how do you want to market yourself? And also some people, I've done really specialized role in my career where I'm doing really deep research on a specific problem, but I also personally like to be more breadth over depth. Sometimes I want new challenges, I want variety. And so I think it's, you know, comes down to a personal choice as much as it does, you know, like a marketability, you know, choice for the particular person who's looking for a job. Other perspectives from the team? No?
Okay, well then I think we'll let you all go. You've given us a ton of your time, and I really appreciate it. Jay, it's good to see you again. I wish we could be hanging out, but this is the world. So, all right, thanks everybody. Like I said, I will be sending out the quick questionnaire shortly for you to mark your attendance. That'll be open until the end of the weekend. People who are asynchronously watching, you'll be able to respond, watch at your leisure. And with that, have a good afternoon all. Enjoy your lunch. Yeah, thanks.
Hey, everyone.
Bye.
Take care.